Welcome back to EGE 2013 Statics. This time what we're going to do is an example of a sum of forces working strictly in two dimensions. But over here on the left you see we have an eye bolt there in black. I'll color that in a bit. So there's our eye bolt. There's three forces acting on this. In blue we have a rope that goes over a pulley or something, and this pulley is located 3 meters in the X direction, 5 meters in the Y direction. In purple, we have a connection through a spring going right here, and the spring has a spring constant of K equals 10.0 newtons per centimeter. And we have also hanging from this hook, we have a weight that is 10 kilograms just hanging straight down in red, okay? So let's start sorting this out. We want to find the resultant force, magnitude and direction, as well as the X and Y components, so we know what kind of load are being placed on our wall back here. So we want to figure that out. So we're going to first put each of the individual forces into our Cartesian format. So we have a force in the X direction, force in the Y direction. We'll sum up all those forces, and then once we have it in Cartesian format, we can calculate the angle and the magnitude of the resultant. So starting at the top, and I also see I failed to label this. No, I didn't fail to label that. Okay. We don't know the angle here, theta. Okay, we want to find that. Well, we know that it goes over 3 meters and up 5 meters. So we have a position vector that we can find here. Or we can just calculate the angle from using inverse tangent. I think that's probably easiest. So we can say that theta equals inverse tangent of our Y direction 5 over our X direction 3. And that comes out to be 59.0336436792648 degrees. Okay, did I just do something ridiculous here? Indeed, I did. Okay. Really, looking at most of these numbers, what I could have done here, what I probably should have done for the beginning, was I should have labeled this 5.00 and 3.00 just to be consistent. Most of these numbers, I have 3 significant digits, right? 12.0. We'll pretend that was that way from the beginning. So I'm telling you, because I said 5.00, that I have 3 significant digits. I kind of know things to about within 1%. It could be 5.02, it could be 4.96 meters. We really, or 4.0096. No, 4.9. Well, whatever. It's going to be off, right? There is no such thing as that exact measurement. So when I try to do this calculation, carrying it out to 1, 2, 3, 4, 5, about a dozen or so spaces, dozen or so digits is ridiculous, right? So I've got 3 significant digits everywhere in my drawing. I'm going to work to 3 significant digits, period. Okay? So let's erase that, and then we're going to say that my angle is 59.0 degrees. Okay? And my magnitude, I already know, is 12 newtons. So I can calculate the force in the X direction. We'll call this A. So AX, or my vector of the force in the X direction, is my magnitude times the cosine of my angle, which is 59.0, and times I, and that's equal to 6.18 I, okay? And AY is equal to 12 sine of 59.0 J, equals 10.3J. And that's that one in Cartesian coordinates. Now we have our spring down here. Well, I know I have a spring constant of 10.0 newtons per centimeter. That, if you recall from springs, that spring constant says every centimeter I extend that, my force goes up by 10 newtons, extended 3 centimeters, so I can take my 10.0 newtons per centimeter times 3.00 centimeters, and I get 30.0 newtons is my force. Okay? And I have this at an angle of 60 degrees here from the vertical. Let me see where I've drawn it. Now I can do a lot of, this is going to get a little bit messy. I can't just say that my AX is 30 times the cosine of 60 degrees, because the cosine of 60 degrees is really in that direction, right? So what I really want is the force in this direction for my X component. So that's going to be actually 30 times, or excuse me, yeah, 30 times the sine of the 60 degrees. So it's, you know, we've labeled our angles a little strange, but we just have to deal with that as engineers. So we'll call this B. X equals my 30 times the sine of 60 times I equals 26.0 I newtons, and these are newtons as well, the force. And By is equal to 30, and actually, because it's downward to be consistent, I'll make that a minus 30. I could try and, you know, work out the angles and get things, but I got to put a minus sign somewhere, so I'll put it in there just by inspection. Cosine of 60J, and that's equal to minus 15J newtons. And my mass over here is 10.0 kilograms, and it's hanging straight down. So I got to go from kilograms to newtons, and we assume that we're on the surface of the Earth here, and we have a standard acceleration of 9.81 newtons, or excuse me, newtons, 9.81 meters per second squared. I can take my mass, I'll calculate my force due to the mass, F sub m, and that's going to be equal to 9.81 meters per second squared times 10.0 kilograms, and that's going to be 98.1 newtons. And we happen to know that this is, all of the force is down, so my F sub m y equals minus 98.1, the vector there, 98.1 J newtons. Okay? So now I can put these all together, just sum everything up. I can calculate my resultant vector, we'll call that R. So my vector R, if I sum up all of the X components, I've got 6.18 plus 26.0 plus 0, so I don't need anything there, I, plus, in the Y direction, I have 10.3 plus, actually it's a minus 15, not minus 15, and minus 98.1 J, and that gives me my resultant vector equals 32.2 I minus 114 J Those are vectors. And if I calculate my magnitude R, the scalar magnitude of that resulting force, it's just square root of 32.2 squared plus 114 squared, and that comes out to 118 newtons, and my angle theta equals tangent minus 1, inverse tangent of the y, which is minus 114 over 32.2, and I come up with a negative 74 degrees. And I'm going to slide this down a little bit, see if I can't get those numbers to stay on the screen. There we go. Okay, so if I draw my picture here, if this is my wall, this is my eye bolt. Okay, so here I have a force of 32 in that direction. I have a force of, and this is not the scale, minus 114 in that direction if I care about the specific forces X and Y, and I have my resultant force here that is 118 newtons, and the angle here is 74 degrees. And that's it. That's the whole problem. Okay? So, simple enough. Bye.